This conference will now be recorded.
with our session. So this course is basically an interview preparation interview preparation course, where we will be discussing the questions, the questions which are asked in the interviews. So those questions and answers will be discussed in this course. So for all topics, so the course will be like each week we will be covering one topic. So like the first week we will be covering scan insertion, then scan compression, then ATPG simulations, and then like JTAG, boundary scan, IJTAG, BIST, wrappers. So hierarchical scan. All these things will actually be covered in the questions of all these topics will be covered in this course. The most frequently asked questions in the interviews, it will be covered in this course. So today's session, it is actually a demo session where we will be discussing sample questions from each topic. So I have selected a few topics and I have prepared some sample questions in each of those topics. And this is a demo session. So it's an overview session, like how the actual session will go. So today we will discuss few questions from, I've selected a few questions from all the topics and we will be discussing those questions. From next week, it will your original course will actually start, where we will be focusing, where we will be taking one topic and we will be covering that particular topic in that week. So Saturday and Sunday, we will be taking one topic and covering all the possible interview questions in that particular topic. So this is how this interview preparation course will go. So now let us start with our demo session. So the very first question the interviewer might ask is, what is the difference between DFT engineer and functional verification engineer? So this is an important question which most of the interviewers ask. What is the difference between DFT engineer and functional verification engineer? So for this question, in order to answer it, you can give a few points, and in order to justify your point, you can tell with the help of an example. So in that case, the interviewer, you'll be able to satisfy the interviewer. So first, what you can tell is you can give few points. You can first tell few points, and then in order to justify your statement, you can take an example and then justify it. So here, basically, as we all know, DFT engineers, we don't check the functionality of the chip. DFT engineers do not check the functionality of the chip. So what do we check? We rather check the quality of the chip. Rather check the quality of the chip. So what is checking the quality of the chip mean? That is, we are going to insert some structures into the design to facilitate the detection of manufacturing defects in the chip. So if any after manufacturing, if some defect occurs, so we can tell that the chip is failing, and apart from that, we can tell what manufacturing defect has caused the chip to fail. So this is what DFT engineers do. DFT engineers do not check the functionality of the chip, we rather check the quality of the chip. So what basically DFT engineers we do is, DFT engineers insert structures into the design, to facilitate the detection of manufacturing defects in the chip. And DFT engineers have more controllability and observability on the design. Have more controllability and observability on the design. So this is because we go for scan insertion, and hence we have more controllability and observability on the design. So as we have more controllability and observability on the design, we take less time to test a chip. Less time to test a chip. And DFT engineers, we also take less patterns. So DFT engineers require less test patterns to test a chip. So in order to justify the first three statements, I'll give you one example. In order to justify this fourth statement, what you can say is, so if we consider the example of AND gate. So in AND gate, as we know by fault simulation, we would have seen. So we will require these three patterns. Okay, for an AND gate, we need only these three patterns: 0, 1, 1, 0, and 1, 1. These three patterns detect all the faults. So even if you don't know like how I'm writing this, no worries. So we will be discussing it during our ATPG class. Okay, how to decide which pattern will detect the faults. So we will be discussing during the ATPG class. So just for an example, I'm telling now. So for an AND gate, 0, 1, 1, 0, 1, 1, these three patterns are sufficient to detect all possible manufacturing defects in this AND gate. Detect all possible manufacturing defects in this AND gate. So the pattern 0, 0, 0, 0, it is actually redundant pattern. So tool will not write it in the final pattern list. Tool will not write it in the final pattern list. Okay. So that's why whichever patterns it will detect all the manufacturing defects, only those patterns the tool will place it in the final pattern list. So in this case, in the case of an AND gate, only these three patterns are sufficient to detect all the manufacturing defects in the AND gate. If it was functional verification engineer, then they also need to write the 0, 0 pattern also they need to check in order to check whether AND gate is functioning properly or not. If it was functional verification, they need to check for all the four patterns. Whereas for DFT engineer, in order to check whether there is any manufacturing defect in the AND gate, these three patterns are sufficient. So that is why whichever pattern detects all the manufacturing defects in our chip, only those patterns the tool will place it in the final pattern list. Hence, DFT engineers, we require less test patterns to test the chip. So this is an example to justify the fourth point. The first 3 points, in order to justify the first 3 points, let me consider an example. So you can consider an example here. So you are having a, so this is your design actually, in your design. you are having a 10-bit counter. You are having a 10-bit counter. Then you are having a counter initialization circuit. Counter initialization circuit. And then counter observation circuit. So this is your design. So in the design, you are having a 10-bit counter, then you are having a counter initialization circuit, and we are having a counter observation circuit. So 10-bit counter, it is going to count from 0 to 1023. So say for example, if suppose counter is failing, this counter is failing. So the reason for the counter to fail is after 999, counter still counts 999 instead of 1000. Counter still counts 999 instead of 1000. So this is the problem. Okay, there is a counter. So counter after 999, it is still counting 999 instead of 1000. So this is why the counter is failing. So now if you consider functional verification engineer, then they can tell that this counter is failing. They will require more than 1000 clock pulses to tell that this counter is failing. Okay, functional verification engineer, they will require more than 1000 clock pulses to tell that the counter is failing. So require more than 1000 clock pulses. 1000 clock pulses to tell that the counter is failing. Why they require more than 1000 clock pulses? Because they are actually, so the reason is functional verification engineer, they are going to check the functionality. They check the functionality. So this counter, when it is failing after 999, instead of 1000, it is still counting 999. That is, at the 1000th pulse, this counter is failing. Okay, counter is failing at the 1000th pulse. So after 999, at the 1000th pulse, it is still counting 999 instead of counting 1000. So counter is failing at the 1000th clock pulse. Okay, and they also require some clock pulses are also required. Some clock pulses are required for counter initialization and counter observation. Counter initialization and counter observation. Okay, so functional verification engineer, they check the functionality. So when is the counter failing? At the 1000th pulse only the counter is failing. So the counter has to count till 1000th pulse. So only then they can tell that the counter is failing. Okay, and they also need some cycles for counter initialization and counter observation. So therefore we can say that functional verification engineer, they require more than 1000 clock pulses to tell that the counter is failing. The same thing if you see DFT engineers. If you see DFT engineers, they can tell that the counter is failing. As we have more controllability and observability on our design, as we have more controllability and observability on our design, more controllability and observability on our design, we can tell that the counter is failing in approximately 100 clock pulses. Okay, we have gone for scan insertion, hence we have more controllability and observability on our design. So we can tell that the counter is failing in approximately 100 clock pulses. Okay, approximately in the range of 100 clock pulses, we require to tell that the counter is failing. So how means in the above example, if we give like this, insert test logic hyphen max length 100, hyphen max length 10, which means in one scan chain we can have 10 flops. Okay, in one scan chain we can actually have 10 flops in it. So how many clock pulses are required? So like pattern 1 loading, you will require 10 clock pulses. So number of clock pulses required during shift will be equal to the number of flops in that particular scan chain. So in one scan chain we are having 10 flops. So pattern 1 load, we require 10 pulses. Then pattern 1 capture, we require 1 pulse. Then pattern 1 unload, and pattern 2 load, we will require around 10 clock. We will require 10 clock pulses. It's the next shift phase. So we will actually require around, we will approximately need around 6 to 7 patterns. Okay, 6 to 7 patterns to detect that, like find the counter is failing. Why? Because each and every net has to be toggled. So with 1 or 2 patterns we cannot toggle each and every net. So we approximately require 6 to 7 patterns to find out that the counter is failing. So here if you see, next thing is like pattern 2 capture, you will require 1 pulse, and pattern 2 unload, pattern 3 load, you will require 10 clock pulses. In the same way, pattern 3 capture, you would require 1 clock pulse. So this, if you are not able to understand, no problem. This is a scan chain operation. So I will be explaining it during the scan insertion class as well, how I am writing these clock pulses. Okay. So first we have the shift phase, where we'll be loading the pattern. Then we'll be having the capture phase. Then in the next shift down phase, we will be unloading the old pattern and loading the new pattern. So that is what I'm writing here. Then this is like pattern 3 unload, pattern 4 load. You will require 10 pulses. So and then pattern 4 capture, pattern 4 unload, pattern 5 load. You will require here 10. Then this is like, let me just write it below. So pattern 5 capture, pattern 5 for pattern 5 capture 1 pulse, pattern 5 load, pattern 5 unload, pattern 6 load, you will require 10 clocks. Then pattern 6 capture, you will require 1 pulse, pattern 6 unload, and pattern 7 load, you will require 10 clocks. So totally here you are having 21, then 11, 11, 11, 11, 11. So 55 plus, so 11 5s are 55 plus this 21, this will be 6, 5 plus 2 7, around 76 pulses. So that is what I have given. Approximately you can write it as in the range of 100 clock pulses, in the range of 100 clock pulses, depending on how much pattern we require. Approximately I consider like 6 to 7 patterns. We might sometimes it might even go like 10 to 15 patterns like that. But the range of clock pulses, it will be approximately in the range of 100 clock pulses only. Okay, like in the hundreds, like around like this 76 or 100 or maybe some 115 like that. Okay, but functional verification engineer, how many clock pulses they require? They required more than 1000 clock pulses. But whereas DFT engineers, we require only in the range of 100 clock pulses to tell that the counter is failing. Okay. So we approximately need 6 to 7 patterns to detect that the counter is failing. Counter is failing, as each and every net has to be toggled. Each and every net has to be toggled and observed. Toggle and observe. So as we have more controllability and observability on our design, we require less clock pulses to tell that our counter, our design is failing. Okay, and because we require less clock pulses, our test time is also reduced. Okay, our test time is also reduced because of this only, as we require less number of pulses to tell that our this is failing, our test like our chip is failing. We will require less test time to test our chip. And we also go for various compression techniques as well in order to further reduce our test time. Okay. So because of this, so as we have more controllability and observability on our design, our test time is reduced. As we have more controllability and observability, on our design, and as we go for compression techniques, and as we go for compression technique, our test time will reduce. Our test time will reduce. And one more important point is, functional verification engineer, they can only tell that that particular counter is failing. But DFT engineers, we can additionally tell that DFT engineers can additionally tell what manufacturing defect has caused the counter to fail. What manufacturing defect has caused the counter to fail. So what can be the possible manufacturing defects? That is the example like MSB net, okay, has stuck at 0. So that MSB net, that is stuck to 0. So that is why when the 1000th clock pulse come, it did not rise to 1. That is why the counter, after counting 999, it is still counting 999 instead of 1000. So the MSB bit net, it can have a stuck at 0 fault. It might be like tied to 0 during manufacturing. Or MSB net can have a slow to rise fault. MSB net can have a slow to rise fault. Okay, before the 1000th pulse comes, and when the 1000th pulse had come, the MSB net did not rise to 1, and so the counter was counting 999. After some time it will get risen to 1. It is slow to rise fault. So when the 1000th pulse had come, the MSB net had not risen to 1. It was still counting, it was still 0. So that is why MSB net, that is why the counter like it can have a slow to rise fault. So what manufacturing defect has caused the counter to fail? That also DFT engineers we can give the additional information. Okay. Whereas functional verification engineer, they can only tell that the counter is failing. But DFT engineers, we can tell that the counter is failing in less number of clock cycles, and we can also additionally tell what manufacturing defect has caused the counter to fail. So this is only the difference between the DFT engineer and the functional verification engineer. So this is an important question which most of the interviewers ask. So this is how you can address the question. So first you can give your points, that is like DFT engineers, we do not check the functionality, we check the quality of the chip. That is, we check whether there is any manufacturing defects in the chip or not. And what do DFT engineers do? We insert some structures into the design to facilitate the detection of manufacturing defects in the chip. Okay. And DFT engineers, we are having more controllability and observability on our design. So we take less time to test the chip compared to functional verification engineer. And DFT engineers, we also require less test patterns to test the chip. So in order to give this example, you can tell that for an AND gate, for functional verification engineer, they need all 4 patterns, 0001, 1011, all the 4 patterns functional verification engineers require in order to tell that the AND gate is functioning properly or not. But DFT engineers, with just these 3 patterns, it is sufficient that 011011, with just these 3 patterns, it is sufficient to detect all the manufacturing defects in the AND gate. And hence, our tool, it will keep only these 3 patterns in the final pattern list. So, DFT engineers require less test patterns to test the chip. And in order to justify the above 3, you can take the example like this. You can take any example. I'm just giving one sample example. You can take any example of your choice and you can explain. So in the example which I had, so I had a counter, a 10-bit counter. So a counter initialization circuit and a counter observation circuit. So if suppose the counter is failing, that is after 999, at the 1000th pulse, it is still counting 999 instead of 1000. So you can tell how many clock pulses does functional verification engineer require. So functional verification engineers, they are going to check the functionality. So counter is failing at the 1000th clock pulse. So counter has to count it till 1000 clock pulses. So 1000 clock pulses are required there. And they also require some clock pulses for counter initialization in order to bring it to the initial state. They require some clock pulses and some clock pulses are required for counter observation. So altogether, functional verification engineer, they require more than 1000 clock pulses to tell that the counter is failing. But whereas DFT engineers, we have more controllability and observability on our design. Why we have controllability and observability on our design? Because we have gone for scan insertion. As we have gone for scan insertion, DFT engineers, we have more controllability and observability on our design. So we can tell that the counter is failing in approximately in the range of 100 clock pulses. So how means in the example, if we just give as, if we have just given as insert test logic hyphen max 10, then in that case, in one scan chain, you will have 10 scan flops. So totally, we will require around 6 to 7 patterns, in the range of 6 to 7 patterns to detect that the counter is failing, because each and every net has to be toggled and the value has to be observed. So that is why within 1 or 2 patterns, we will not be able to find out. So at least like in the range of 6 to 7 patterns might be required. So if you see from the above calculation, we will require approximately the range of 100 clock pulses to tell that the counter is failing. But functional verification engineer, they had required more than 1000 clock pulses. So we will require in the range of 100, but functional verification they will require more than 1000 clock pulses to tell that the counter is failing. So we are able to tell it in less number of clock pulses because we are having more controllability and observability on our design. So that is why as we require less number of clock pulses to tell that the counter is failing, and also as we are going for various compression techniques, we will our test time is actually less. Okay, the test time compared to functional verification engineer is actually less. And DFT engineers, we can also additionally tell what manufacturing defect has caused the counter to fail. That is the MSB net. It can be stuck at 0, it is tied to 0, or it is having a slow to rise fault. So when the 1000th clock pulse had come, the MSB net did not rise to 1, it was still 0. So that is why after 999 it was still counting 999 instead of 1000. So additionally, we can tell what manufacturing defect has caused the counter to fail. So this is how you can answer this question. What is the difference between functional verification engineer and DFT engineer? Give some statements, and then to justify your statement, you can explain it with the help of an example. Okay. So this is one of the important question which most of the interviewers ask. So we have a functional verification team. Then what is the necessity of DFT team? So this can also be this question. So this is the same answer. Difference between functional verification engineer and DFT engineer they can ask, or else they can even ask like we are having functional verification team in order to test the chip. Then why do we need DFT team? Okay, so this is the same answer we need to give for both the questions. Okay. So this is the first question. And we will go to the next question. So today is just like an overview session. So I have prepared few questions from each topic. Okay, from scan insertion 1 or 2 questions, from compression 1 or 2 questions, like that. From each topic, I have just prepared 1 or 2 questions in order to just give a demo. This is a demo session actually. So from the next week onwards, we will be having a full-fledged session where we will take one topic per week and we will cover most of the interview questions in that particular topic. So from next week we will start, like next week we will complete scan insertion. We will take scan insertion and complete all possible interview questions in that, like most of the possible interview questions in that particular scan insertion topic. We can cover it in next week's class. Then the next week will be covering compression, like that. So today is a demo session where I'm just giving you an overview of how the course will go. So this was the first question. And the second question is like, this is a very easy question. So what is scan insertion? What basically happens in scan insertion? So what is scan insertion? So what happens in scan insertion? So this is a very simple question. All the normal flops, it will be converted into scan flops and it will be stitched into a scan chain, which is the Q to SI path. Okay. So all normal flops are converted into scan flops and then stitch all the scan flops into a scan chain. So in order to bring the Q to SI path. And what is the need of scan insertion? As we discussed above, in order to gain controllability and observability of the design. So what is the need of scan insertion? So to gain controllability, and observability of the design. So what is gaining controllability and observability of the design? In order to tell that, you can give the example, you can give the counter example. So like not only this counter example, any other example of your choice also you can give. A similar kind of example you can tell. And you can tell that we are having, in order to gain this controllability and observability of our design, we are going for scan insertion. And how with the help of scan insertion you gain controllability and observability? You can explain an example as I had told about the counter example, you can explain it. And then the various other questions which can be asked in scan insertion which are important is the scan insertion flow. So I'm just telling the question. In the next week we will discuss all these things. The scan insertion flow, okay, the lab practical scan insertion flow. Then scan chain operation, how the scan chain operates, like what happens during shift phase, what happens during capture phase, all those things. And those things also you can explain with the help of an example as well. So we'll discuss all those things in the next week's class. Then the various scan DRCs. So clock controllability DRC, set reset controllability DRC, bus contention, then combinational feedback loop, then potential race condition. All these things are some of the DRCs. And Exos DRC. All these things are some of the DRCs. And the another important topic is edge mixing and domain mixing. So why do we need to go for edge mixing and domain mixing? What is balancing? So why do we need to go for balancing? And what are all the problems which you face during edge mixing and domain mixing? How will you resolve the addition of lockup latches? So that's what. So that is also an important topic which many interviewers actually ask. And how do you take care of latches in your design? So if there are some latches, so how will you take care of that? So that is one interview question. And okay, so yeah, and why do you declare reset as a clock instead of pin constraint? So those kind of questions can be asked in scan insertion topic. So we will discuss those things in the next week's class, where I will be taking one topic and covering that topic, covering the most possible interview questions in that topic during that session. Okay. Uh, yeah, this is regarding scan insertion, and this is just an overview session. That's why few questions alone I have taken. Then coming to compression. So like, what is the need of scan compression? What is the need of scan compression? Okay. So what is the need of scan compression? So basically, scan compression, it is actually required to reduce the test time, reduce the test time, reduce the test time, and to reduce the test data volume. This is why we require scan compression, to reduce test time and to reduce test data volume. So with this point, you can even take an example and you can like explain with the help of an example how with compression our test time will reduce and our test data volume will reduce. So if you consider, like, the first thing which we'll see is test time reduction. Test time reduction. So there is actually a formula for test time. So Can anyone like put in the chat box like what is the formula for test time? How to calculate test time? You can put it in the chat box. So if you know. So the formula for test time is number of patterns into number of shift cycles per pattern. And yeah, one more thing, like if you want to message me personally in this go-to meeting, please put the chat on Vidisha underscore laptop, because in the other account I will just be writing, I will not be checking the chats. So please put the chats in Vidisha underscore laptop, or else you can put to all organizers or everyone. So the formula for test time is number of patterns into number of shift cycles per pattern, number of shift cycles per pattern into clock period of scan. Clock period of scan. Patterns into clock count into time. Yes, correct. So number of patterns into number of shift cycles per pattern into clock period of scan. So this is the formula for test time. Now you can consider without compression, and with compression, without compression and with compression. So the number of patterns without compression will be less. Number of patterns without compression will be less. So I'll consider as 1500 here. Here with compression, the number of patterns I will consider something as 2000. Why with compression the number of patterns actually increases? So there is a concept called as fault aliasing, which I will be discussing during the ATPG class. There is a concept called as fault aliasing, and because of that, the number of patterns it will increase when we go with compression. Okay. So as of now, just remember like number of patterns without compression will be less compared to number of patterns with compression. The reason is because of fault aliasing. I'll be discussing that during the ATPG class. Then number of shift cycles per pattern. Number of shift cycles per pattern. Number of shift cycles per pattern. Without compression, it will be more. And with the compression, it will actually be less. Shift cycles per pattern. So with compression it will be less. So why this is like this, that also I will tell it to you logically when we are covering the EDT class. While we are covering the EDT class, I'll tell you logically why number of shift cycles per pattern it will reduce when we go for compression. And then clock period of scan clock. clock period of scan clock. I will keep it something as 20 nanoseconds here, and here also clock period of scan clock, it is going to be same, clock period of scan. So just an example I have considered. You can take your own example actually. So now the only thing which you need to remember is number of patterns with compression will be more. That is because of fault aliasing. And number of shift cycles per pattern with compression it will be less. So that I will tell you during EDT class. I'll tell you logically why number of shift cycles per pattern it will be less with compression. So you can substitute in the above formula, the test time formula, you can substitute this for both without compression and with compression, you can substitute it, and you can tell me the answer, you can put the answer. So in nanoseconds, so in milliseconds you can give the answer. Okay, you can give the answer in milliseconds. So just substitute all these values in the above example. Then for without compression and with compression, you can give me the test time in milliseconds. So we can see that with compression test time will reduce. So you can calculate it and put it in the chat box. You can message to either Vidisha_laptop or to organizers or to everyone. Yes, correct, Fanindra. So how about others? You can also put your answer. Yes, correct. Yes, correct. Armani. So here you need to just substitute these values. Number of patterns will be 1500, number of shift cycles per pattern will be 500, and then clock period of scan clock will be 20 nanoseconds. So now if you just simplify everything, then you'll be getting this as 15 milliseconds. And here you have to just substitute this one. Number of patterns is 2000, number of shift cycles per pattern is 50, and this is 20 nanoseconds. So this will be 2 milliseconds. So if you see, test time with compression is less compared to without compression. So this is how you can tell that with one need of compression is to reduce the test time. Same way we can do for test data volume. So, test data volume reduction. So test data volume is, the formula is number of patterns number of shift cycles per pattern into number of channels. So this is the formula for test data volume. Number of patterns into number of shift cycles per pattern into number of channels. So same way, without compression and with compression we can do it. Without compression and then with compression. So here number of patterns, it will be like slightly less compared to with compression. Same example, we'll consider 1500. Here we will consider 2000. And then number of shift cycles per pattern, here it will be like more. This I will explain logically how it is when we are covering EDT class. And number of shift cycles per pattern with compression will be pattern. So this will be 50. And number of channels, it will be the same. Yes, I'll tell that like how number of shift cycles per pattern it will be reduced with compression. While we are covering the EDT topic, I will explain it to you logically. So how the shift cycles per pattern will reduce. So this is just a demo session, so that's why I directly written. While we are covering the interview questions of scan compression topic, I'll explain it to you logically how number of shift cycles per pattern will reduce. Okay. Or I'll just explain. Okay, I will just explain after this question. So how shift cycles per pattern will reduce with compression. So I'll just explain this point after this question. So number of channels, it is number of external channels with compression and without compression, it is going to be same. So number of channels. Now in this test data volume, you can substitute it in the formula, and then you can tell me in terms of megabytes. So what will be the answer? Okay, so after this question, I'll just explain how number of shift cycles per pattern will be reduced with compression. So I can just substitute in this formula and you can tell. Aditi, your answer is correct. So this, if we just substitute it, this will be 1500 into 500 into 2. So this will actually give us 1.5 MB if we simplify it. And then this one, if we just substitute it, 2000 into 50 into 2. So test data volume will be 0.2 MB. So this is how we can tell that the with compression, like test data volume is actually reduced. So why the number of patterns will actually increase in compression? There is a topic called as fault aliasing, which I will be covering during ATPG class. This one, why number of patterns it actually increases with compression. So now I will just tell you how the number of shift cycles per pattern actually decreases when we go for compression. Okay, when we go for compression, how number of shift cycles per pattern decreases. So we will see here. Question number 5. So how number of shift cycles per pattern, shift cycles per pattern reduces when we go for compression. So we will first logically analyze this one, logically analyze some scenarios, and yeah, then we will come up to a conclusion how number of shift cycles per pattern it will reduce when we go for compression. So I will give three cases. So case one. So you just assume an example. Take an example here. In this example, we are having total 5 lakh flops in the design. 5 lakh flops in the design. We are having a total of 5 lakh flops in the design. Now in case, I'll give three cases. So in case 1, there are 2 scan chains in the design. 2 scan chains in the design. So in one scan chain, How many flops you will be having? You will be having 2,50,000 flops in one scan chain. Now in case 2, we are having 50 scan chains. 50 scan chains in the design. So in one scan chain, we will have 10,000 flops. Now in case 3, we are having 100 scan chains. 100 scan chains in the design. So in one scan chain, we will be having 5,000 flops. Now as you know, test time, the formula for test time is number of patterns into number of shift cycles per pattern, shift cycles per pattern into clock period of scan clock. So now just analyze these three cases and tell me for which of these three cases test time will be least. For which of these three cases test time will be least. The least. So analyze these three cases and tell me like in which case test time will be the least. So how about others? Can you also tell your viewpoint? Like in which of these three cases test time will be the least? Side. Yes, correct. Yes, correct, Sunanya. So in case 3, test time will be least. Case 3, test time will be the least, as the number of flops in the scan chain, as the number of flops per scan chain is less in case 3 compared to other two cases, compared to other two cases. Hence, number of shift cycles per pattern, it will be least for case 3. Number of shift cycles per pattern will be the least for case 3. But there is actually a disadvantage in this case 3. there is actually a disadvantage in this case 3. So the problem is like disadvantage of case 3. So what is the disadvantages? If we need, in case 3 we had 100 scan chains. So if we need 100 scan chains in our design, we need 100 scan chains in our design, then we require 100 scan in, 100 scan in and 100 scan out ports from top level. So it is like this. So this will be like this. So if you have 100 scan chains, then you will require 100 scan in and 100 scan out port. Scan in 1, scan out 1, then this is scan in 2, scan out 2, so on, and scan in 100 and scan out 100. But the number of ports from top level, it will be limited. Number of top level ports will be limited. Okay, number of top level ports, it will actually be limited. So if we have like limited number of top level ports, so like if we stitch it into like just 2 scan chains, then in that case we are consuming less number of ports from top level. But the problem is, if you have only 2 scan chains, then in one scan chain you are having 2,50,000 flops. So 2,50,000 shift cycles will be required per pattern, and hence test time will actually increase. So what is our problem? Like if we have two scan chains, then the number of ports from top level is reduced, but the test time is actually increasing. If we go for 100 scan chains, then our test time is reducing, but the number of ports from top level is increasing, which is like not possible. It is not possible to have 100 scan-ins and 100 scan-out ports. So total 200 ports from top level and all, it is not possible to get. So what we will be doing is, in order to overcome the disadvantage of case 3, in order to overcome the disadvantage of case 3, we go for scan compression. Okay. So what will happen is, in scan compression, what we are actually going to do is, from top level, scan channel, that is nothing but an external channel, we call it. External channel will be internally divided into multiple scan chains. Internally divided into multiple scan chains. So how it will be there is, we'll be having a decompressor logic. We'll be discussing about this, what is decompressor logic, what is compressor logic, those things we'll be discussing it in depth during the EDT class. This is a decompressor, this is a compressor. So from top level, we will be having, like say for example, we are having only 2 channels from top level, which will be divided internally into 100 chains. This is 1 to 100 scan chains. So this is these are actually the internal chains. These are the internal chains, and these are the external channels. External channels. Now if we go for compression, okay, so now if we go for compression, like if we don't go like without compression, if it is without compression, then from top level only two channels are there, so you will require 2,50,000 shift cycles per pattern. Now if you go for with the compression, then in one scan chain you will be having only 5,000 flops. Okay, with the compression you will be having only 5,000 flops. So 5,000 shift cycles plus few more additional shift cycles also will be increased, like number of bits in the masking logic and initialization cycle, which is the seal of decompressor logic by external channel. So I will discuss that how the number of cycles with compression it will. So number of shift cycles with compression, how it is decided. So I will discuss it during that EDT class actually. So but it will be like less compared to without compression. So this is why with the compression the number of shift cycles per pattern will be reduced. Okay, so without compression in this case, that means if you don't have this compressor and decompressor logic, without compression only with the top level ports, you will require 2,50,000 shift cycles per pattern. But with the compression, 5,000 plus few more clock pulses you will actually require. So that I'll tell you how to decide it. I'll tell you during the EDT class. So in the range of 5,000 only you will be getting. So this is how with compression the number of shift cycles per pattern is decreasing. And also we have also overcome the problem of limited number of ports from the top level. So this is why we go for compression. Okay. Uh, so we'll see the next question. So I'm having number of external channels. External channels is 2. Number of external channels is 2. And compression ratio is 50x. Now calculate the number of internal channels. How many internal channels will be there in the design? Internal chains. Okay. So there is a formula for compression ratio. These kind of questions also they can ask, this compression ratio formula type question. So compression ratio is equal to number of internal chains divided by number of external channels. Number of internal chains divided by number of external channels. So you can calculate this and tell me how many internal chains are required. So this X basically stands for how many times chains are compressed into channels. X stands for how many times chains are compressed into channels. So you can calculate it and you can put the response in the chat. Yes, correct, Arunadipti. And Pujita, your answer is also correct. So here compression ratio is 50x, number of internal channels we do not know, and number of external channels is 2. So this question mark, this is nothing but number of internal chains is equal to 50 into 2, which is equal to 100. So 100 internal chains. And we'll see the need of decompressor logic, what is there inside the decompressor logic, like the LFSR logic, phase shifter logic. What is the need of LFSR, what is the need of phase shifter, so why do we need a compactor, what is the need of masking logic. So those kind of questions we will cover it up in the EDT class. And also how do you like what is the need for going for EDT bypass, what is one hot decoder, what is X masking decoder. So those kind of questions we can discuss it, we can expect in EDT, and we can discuss those things in the what is it, in the original, like when we are discussing EDT topic, right? At that time we can discuss it. So I'll just ask one question from EDT. So what is the need of masking logic? So this is question 7. What is the need of masking logic? In the same way, we can discuss all the other things need. What is the need of decompressor? What is the need of compressor? So in the same fashion, we can discuss it for all the other logics which are there in the EDT logic. So basically, the need of masking logic, we will be using masking logic to to stop the propagation of X. Stop the propagation of X. Okay. So basically, in compressor, this is our compressor logic. We'll discuss it in depth. Okay, each logic need we will discuss it during our EDT class. So as of now, just remember that this is a compressor logic. So here you'll be having the internal chains like this. Yes, correct. So correct. In order to stop the propagation of X, we are going for masking logic. Yes, Abhishek, your answer is correct. So in compressor, we will be having levels of X source like this. And say for example, this scan chain is propagating X. The other scan chains are all propagating proper value. Now when one input of the XOR is X, the output of the XOR will be X. And here the output of the XOR will be 1. 0 XOR with 1 is 1. Here what is having? When one input of the XOR is X, the output of the XOR will be X. So what is happening? We are not able to observe. So just because this scan chain is propagating X, we are not able to observe the other scan chains as well, because the output is going to be X. So in order to stop the propagation of X only, we will be going for masking logic. So why do we normally get X's? So we normally get this X, normally get X if there are some black boxes in the design. So like memories or any analog blocks analog blocks and all, we would have declared it as a black box. So if there are any black boxes in the design, so memories or analog blocks, we will be declaring it as a black box, and we need to make sure that during ATPG time, these black boxes have to be bypassed. If we don't bypass the black boxes, then the output of the black box is going to be X. Okay, we normally get X if there are any black boxes in the design, and if the black boxes are not bypassed during age. Okay, so normally the memory is analog blocks, whichever we are declaring it as a black box, so its output will be X. If we don't bypass these black boxes during ATPG time, then it will propagate the X in our logic. So that is why X propagation happens in our scan chip. Okay, so this is just one sample question. We will discuss it in depth, like how masking logic it will stop the propagation of X, and what is the need of mask shift register, what is the need of mask hold register, then what is like X masking, and what is one hot decoder. So those kind of things we will discuss it in depth during the EDT class. So this I have just given an overview of why we require a masking logic. Okay. So these are few questions. These are some questions which can be expected in the EDT topic. We'll cover all the questions in the EDT class, which will when we are discussing it in the when we are discussing the EDT topic. So next, let me give you a few questions from ATPG topic. So okay. So I have considered like there are consider an AND gate, and you have been given only two patterns. So this is 1 1 and 0 1. Only two patterns are actually given for this AND gate. Now tell me, what will be the fault coverage? What will be the fault coverage with these two patterns? What will be the fault coverage of this? What will be our fault coverage? So the formula for fault coverage. So fault coverage you need to find out. So the formula for fault coverage will be number of faults detected divided by total number of faults. Total number of faults in the design. So you have been given only two patterns, 1 1 and 0 1, and you need to tell the fault coverage. So the formula for fault coverage is number of faults detected divided by total number of faults in the design. Okay. So here in this case, design is this aggregate. So you can calculate it and you can tell me the fault coverage. Like you can take some like this is like it requires some calculation, so you can take some 10 minutes and you can tell me the answer. So these kind of questions you can expect it in ATPG. Pujita, you have got it as 33%. Okay, you can just check once again. Like maybe you have made some mistake there. So you can just check once again and you can try once. Do the approach. Yes, correct, Arunaditi. So 83%. So let me just tell you the approach of how you can approach this problem, and then you can just try it once. So total, first you will calculate the denominator. Total number of faults in the design. Total number of faults in the design. So total number of faults in the design. What are all the possible faults it can come? One is like A is stuck at 0, then A is stuck at 1. So you are having two inputs of the AND gate, A, B, and then one output, that is Y. So A is stuck at 0, A is stuck at 1. Then B is stuck at 0, B is stuck at 1. Then Y is stuck at 0, Y is stuck at 1. These are all the possible faults in the circuit. So total how many faults we were having? 6 faults. So 3 things and into 2, so 6. So total we are having 6 faults. Now the denominator we have found out. Now we need to see the numerator. So number of faults detected. Number of faults detected. So you can take each fault. So the rule what you have to do is take each fault, and apply D algorithm. Apply D algorithm to find which pattern, which pattern. Uh, no, fault collapsing is not considered. So without considering fault collapsing. Okay. So take each fault, apply D algorithm to find which pattern will detect that fault. Detect that fault. So first thing is like, for example, A stuck at 0 means, so the pattern which the tool will apply is, this is assume a fault, apply opposite value. So tool will apply 1 here, and in B net it will write a value to propagate that fault to the out observation point. Observation point is the floor. So for AND gate, so this will be like this. So only when one input of the AND gate is 1, the output of the AND gate will be the other input. So in order to propagate the value in A net to the output, that is to the observation point, the tool has to write one value in B net. Okay, only then this particular fault will get detected. So in this way, so one pattern is there, right? So yes, so this fault, it is getting detected. This will get detected. Same way, you check for other thing. If it is getting detected by 1 1 or 0 1, then you have to add it to the numerator. Otherwise, don't add it. So you have to do like that, and you need to see how many faults are there in the numerator. So numerator by denominator, you will be getting the fault coverage. So how we are telling that it is detected, what is good machine simulation, what is faulty machine simulation, those things and all I will discuss it during ATPG class. Okay. The fault simulation thing, good machine simulation, faulty machine simulation. Those topics I will be discussing it during the ATPG class. So today just apply this pattern using D algorithm, and if that pattern is coming, then that fault is detected. So this is how you can approach this question. So let us see the solution. So A stuck at 0 is detected. So one fault has got detected. Now A is stuck at 1, we will see. So we will apply D algorithm and find out which pattern will detect this fault. So assume a fault A is stuck at 1, give opposite value. So opposite value is 0, and the other input the tool will be writing in such a way that the value in the A input will be propagated to the observation point. So B will be 1. So the pattern which will detect B stuck at A stuck at 1 fault is 0 1. Whether 0 1 pattern is there? Yes, it is there. So this fault will also get detected. So total as of now 2 faults have got detected. Next, we will consider this B stuck at 0. So B stuck at 0. So assume a fault. The tool will apply opposite value, and in A net it will write a value so as to propagate that fault, propagate the value which is there in B to the observation point. So A value will be 1. So 1 1 pattern is there. So hence this fault also gets detected. Next, we will see this B stuck at 1 fault. B stuck at 1 fault. So assume a fault, that is B stuck at 1. Apply opposite value. So in the B net it will apply 0. In the A net it will write a value so as to propagate the value in B net to the observation point. So A has to be 1. So 1 0 pattern, that is actually not provided to us. So hence this is not detected. B stuck at 1 is not detected. Then same way Y stuck at 0. Y stuck at 0, assume a fault and give opposite value. So the tool will try to bring one value at Y. So if the tool has to bring one value at Y, then in A, B, the tool has to write 1, 1. Okay, at the inputs it has to write 1. So the tool will try to write 1 on Y net. So the inputs of the and gate has to be 1. So 1 1 pattern is there, and hence this is also getting detected. Now Y stuck at 1. Y stuck at 1. So we'll discuss this D algorithm also. We will discuss when we discuss these fault simulation. All these things also we will discuss during our original ATPG class. And Y stuck at 1. So here the tool will try to bring to assume a fault, so it will try to bring opposite value. So tool will try to write 0 on y net. So the inputs of the and gate has to be, so either A is equal to 0, B is equal to 0, or A is equal to 0, B is equal to 1, or A is equal to 1, B is equal to 0. Any three. So it can be any three. So any of these three patterns can bring a 0 value on the y-net. Okay. So these three patterns can detect the fault, among which 0 1 pattern is all 0 1 pattern is actually given. So this pattern, so with the 0 1 pattern, this fault will get detected. So totally 6 faults were there, out of which this B stuck at 1 fault alone did not get detected. Among this B stuck at 1 fault alone did not get detected. So total we are having 6 faults, out of which 5 have got detected. So our fault coverage will be, total number of faults detected is 5, and total number of faults in the circuit is 6. So 5 divided by 6 into 100%. So this will be approximately 83%. This is the fault coverage. So only with D algorithm I have just found out which pattern will actually detect the fault. So how I'm telling that this fault is getting detected, this fault is not getting detected, and the good machine simulation, faulty machine simulation, all these things, right? I will discuss it during original ATPG class, original ATPG interview preparation class. Okay. So this question you can actually arrange like this. So the next question is. Uh, so I'll give you a circuit diagram. This is A. This is VLC. So this is E, F, L. Then this is H. This is J, and then this is K. So apply the algorithm and find out which all patterns, which all patterns will detect, this is what is it, L stuck at 0 fault. So you can apply. So the answer is the approach is you need to find it by applying D algorithm. So apply D algorithm and try to detect and try to tell which are all the patterns will detect L stuck at 0 fault. That is the value of A, B, C. correct, Phanita. So here, if it is L stuck at 0 fault, so tool will try to write one value on L net. So this is according to D algorithm. Assume a fault, apply opposite value. So if it has to bring a one value here, then this has to be 1. So if this has to be 1, then here B and C it can be 0, 1, or it can be 1, 0, or it can be 1, 1. So any 3 value. And then it will bring 1 here. And in order to propagate, so this is for controlling. This is 1 here. And in order to propagate this value to the output side, this A has to be 1. Okay, A has to be 1, only then the value which is there in this L net will be propagated to the output side. So the patterns which we will detect is A, B, C. Okay, A, B, C. So A it will be 1, B will be either 0, 1, 1, 0 or 1, 1. So these are the 3 patterns. So these 3 patterns it will actually detect the L stuck at 0 fault. So this is how you can approach this question. And in the same way, few more questions like in ATPG, what are all the questions you can expect is, as we have done for stucket, they might ask you like for transition delay fault, they can ask you the pattern, which pattern will detect the transition delay fault, and then the 2 ways of detecting transition delay fault, that is like TDF LOC, TDF LOS, and then what is the difference between transition delay fault model and path delay fault model, and then what is IDDQ test, okay, what is burn-in test, then what else you can expect in ATPG is, mm, yeah, so in OCC also you can expect, so which logic will decide which clock has to be propagated during shift phase and capture phase, and which will also decide the number of clock pulses during capture. So OCC also they can ask. So these are all the important questions which will be asked in ATPG, and yeah, coverage analysis. So how did you improve your coverage? And then the fault classes, okay, and fault categories, fault dominance, fault equivalence, fault collapse, those things, and fault aliasing. So these questions are all important questions in ATPG, which we will be discussing it during our ATPG interview preparation session. So here, as it is a demo session, I have just skipped 2 questions in ATPG 1. So then we will uh, see few questions from advanced topics. So question number 9. Like, what is the need of what is the need of JTAG? So JTAG it stands for Joint Test Action Group. So its standard is IEEE 1149.1 standard. Okay. So what is the need of JTAG in DFT? For DFT, what is the need of JTAG? So in DFT we use JTAG to minimize the number of ports from top level or top level ports, anything. So to minimize the number of ports from top level and to achieve boundary scan. So these are the 2 needs of JTAG, to minimize the number of ports from top level and to achieve boundary scan. So we'll see how, like with the help of JTAG, we are minimizing the number of ports from top level. So to minimize the number of ports from top level. So for example, just consider the following signals. Consider the following signals. So few important signals I've taken a note. Test mode, then EDT bypass enable. The need and usage of all these things, all these signals, I will explain it to you when we are taking the original course. Okay. Then int mode, then you'll have a signal called as ext mode. So we'll have another signal called as int l test enable and ext l test enable. Then we can have like mbist bypass enable, mbist bypass enable, then BIST setup, BIST setup, mbist pg enable. These are all few important signals. Okay, we will discuss it during our interview preparation course. So here I have made a list of few signals. So these are few important signals. Few important signals. So apart from this, there will be many more signals. Apart from this, there will be there will be many more signals. Many more signals like this. Okay. So now if you consider, if all these signals, if all these signals are to be controlled from top level, if all these signals are to be controlled from top level, then number of ports, number of top level ports, top level ports will increase. Okay. So these are some important signals. Apart from this, there will be many more signals like this. If all these signals are to be controlled from top level, then the number of ports in the top level will increase. Therefore, what we do is, therefore, we use JTAG, we use JTAG to internally control these signals. Internally control these signals. Okay. So now when we have used JTAG, we will require only 5 top level ports. The JTAG signals TMS, T clock, T reset, TDI, TDO. These 5 top level ports are required, and of course those EDT channels, those ports are also required. Okay. So all these signals, instead of controlling it from top level, we can use JTAG to internally control these signals. So this is how the number of ports from top level, it decreases when we use JTAG. So how these signals are internally controlled and what is the architecture of JTAG, what is JTAG FSM, what happens in each stage of JTAG FSM, those things we will discuss it during the JTAG topic. Now this is just an overview session, so just a very basic question I have just taken. So what is the need of JTAG? One thing is to minimize the number of ports from top level. So how it is done is by internally controlling the signals, and then in order to achieve boundary scan. Okay. So there is another important point which I'll just make it as a question. So question number 10. So I'll give 4 signals. Okay, consider 4 signals. Consider the below 4 signals. signals. So one is EDT bypass enable. Second one is EDT update. Then third one is test mode, and fourth one is scan again. Okay. So among these four signals, which signals can be internally controlled using JTAG? Which signals can be internally controlled using JTAG? So you can just give it a try. So which are all the signals can be internally controlled using JTAG? Just give it a try and you can put it in the chat box, which you feel that it can be internally controlled, and which are all the signals it has to be controlled from top level. Is the recording media available? Sunanya, it might extend till like 12:30 or 1. You're telling like EDT bypass enable and EDT update, it can be controlled using JTAG. Or EDT bypass enable and test. Okay. Uh, okay. So I'll just tell you the answer. So one point which you need to remember is using JTAG, using JTAG, we can control, we can control only static signals. We can control only static signals. So static signals means the signals that are constant throughout the run. The signals that are constant throughout the run, these are the static signals. So when you consider EDT bypass enable, this is a static signal. This is a static signal. So that is, it will either be 0 or 1 for the complete run. For the complete run. So if it is like, if the run is for bypass, then it will be 1. If the run is with the compression, then it will be 0. So for that complete run, it will either be 0 or 1 respectively. It is with the compression means it will be 0. If it is bypass means it will be 1. So for that complete run, it will either be 0 or 1. If you consider EDT update if you consider, then this is non-static signal. Non-static signal. So why? Because for the same run, during load and load phase, it will be 1. For the rest of the procedures, that is during shift phase, capture phase and all, rest of the procedures, it will be 0. Okay. So this is a non-static signal. So EDT update can't be controlled using JTAG. Can't be controlled using JTAG. We have to control from top level. Okay. And same way, if you consider the third signal is test mode. So the CDT update signal and all, if you are not familiar, no issues. We will be covering it during our EDT class. So while explaining the EDT waveform, we will be covering it. What is the CDT update signal? What is its use? So and also EDT bypass those signals also. We cover all the signals. Okay. And this test mode, it is actually a static signal. Why? Because this test mode, it is going to be 1 for the complete run, because for complete DFT, test mode signal will be 1. So we will be covering each and every signal, we will be covering it. So by the time when we come to the JTAG topic, you will be familiar with all the signals. So just remember that this test mode will be 1 throughout DFT. So for the complete run, this test mode will be 1. So therefore this is a static signal. Therefore it can be controlled from top level. Sorry, it can be controlled using JTAG. Can be controlled using JTAG. If you consider scan enable, then this is a dynamic signal or non-static, not static signal. So scan enable, what will happen is it will be 1 during shift phase, and scan enable will be 0 during capture phase. So this is a dynamic signal. Therefore, it can't be controlled using JTAG. It can't be controlled using JTAG. So we need to control it from top level. So whatever signals I have made a list here, these signals are all like static signals. Okay, for the complete run, this will be like the same value. So all these signals are actually static signals. So all these signals, they can actually be controlled. What we will be doing is, instead of controlling the static signals from the top level, we will be internally controlling the static signal through using JTAG. So how it is done? When we understand the JTAG architecture, you will be able to understand that how these static signals are internally controlled using JTAG. And with JTAG, we will be able to control only static signals. The signals which are changing in the run, which are changing their value in the run, that we cannot control using JTAG, we need to control from top level. So in this case, EDT update and scan enable for that particular run itself they are changing that value, so it cannot be controlled using JTAG. We need to control it from the top level. Okay, so this is what is for JTAG. And then we'll see what is the need of boundary scan. Why do we need to go for boundary scan? So what is the need of boundary scan? So basically, first what will happen, all the chips, it will be tested onto the tester. Individually the chips will be tested on the tester, and then the chips will be placed on the PCB board. So this is the board. First individually, after manufacturing, the chips will be tested on the tester individually. After that, the chips will actually be placed on the board, PCB board. This is the board, and the chips will actually be placed. This is chip 1, this is chip 2, and this is chip 3. So there will be some interconnection between these chips. Just some random interconnections are drawing. So now what can happen is chip 1, chip 2 and chip 3 have all passed their test on tester, that is on ATE. So after manufacturing the chips, it will be individually tested on the tester. Okay, each chip will be tested on the tester. Yeah, chips will be tested parallelly, but each chip it will be tested on the tester. So all chip 1, chip 2, chip 3, they have passed their test on the tester. But when this PCB board is tested, this board is failing. But the board is failing. Okay. Individual chips, while they are tested on the tester, they have passed. After that, they are actually placed on the PCB board, and these interconnections are all formed. Now, when the board is tested, this board is failing. So, this board is failing. This can be due to the manufacturing defects in the interconnection between the chips. Interconnection between the chips. So between two chips there are some interconnections, right? Because of the manufacturing defects in the interconnection between the two chips, this PCB board can fail. So what we do is we go for boundary scan in order to test the interconnection between the chips. So in order to detect the manufacturing defects in the chip, manufacturing defects in the interconnections. Sorry, not in the chip, in the interconnections. In the interconnections, we go for boundary scan. In order to test the manufacturing defects in the interconnection between the chip, we actually go for boundary scan. So in boundary scan, the questions they can ask is what is the structure of boundary scan cell? What are the modes of operation of boundary scan cell? Then what are the mandatory instructions? Like there will be like X test instruction, sample preload instruction, bypass instruction. So those are mandatory instructions of JTAG that will normally be using it during boundary scan test. So those instructions we can ask. And some non-mandatory instructions, but which is actually used in the industries, like what is the use of ID code instruction. So those kind of things can be asked to this boundary scan topic. Okay, so JTAG and boundary scan they actually are related. So the need of JTAG is to one of the need of JTAG is to achieve boundary scan. So we will see those things during our class, during our boundary scan class, how with the help of JTAG we are able to achieve boundary scan, and how with the help of boundary scan, like we are able to detect the interconnection between, detect the manufacturing defects between the interconnections, the interconnection between the chips. So we can see that when we come to the original class. Okay. So now let us uh, see a few questions from MBIST. So, describe the decent memory BIST implementation. Describe the decent memory BIST implementation. So, the decent memory BIST implementation is nothing but I just paste a diagram. Uh, yes, Aruna Dipti, you can tell me like which diagram you want to see.
Yes, ma'am, it's B scan diagram I'm asking about.
Okay, okay, yeah, I can just see.
Just 1 minute, ma'am. I'll noted, ma'am. You can take back to the other page. Thank you.
So after JTAG, we will actually be discussing about IJTAG. There is another thing called as IJTAG. So IJTAG difference between JTAG and IJTAG. IJTAG is 1687 standard. Then difference between JTAG and IJTAG, and then what is the advantage of IJTAG over JTAG. So those kind of questions we will be able to discuss when we understand the architecture of JTAG. So during the original course, after we understand the architecture of JTAG, we will go to the IJTAG standard. Then we will see what is the like in IJTAG. Apart from JTAG, you will be having one additional component called as SIM. So how IJTAG actually operates, and then um, what is the advantage of IJTAG over JTAG. So those things we will discuss, and then how IJTAG network it is used to control the course. So like in our in level 3 project actually, we will be having one core B level. So this will be core B, and inside that 4 core A's will be instantiated. So we will see the IJTAG network in core A level, and see how with the help of IJTAG we are able to internally control the static signals. Then from core B level we will see the IJTAG network, and we will try to understand like it will be very similar, just a replication only with with few small changes. So all these topics we will discuss it during our original interview preparation course. So in order to understand all these things, you need to understand the architecture of JTAG and how JTAG will actually control the internally control the static signals. So we will cover it up when we are dealing with our original course. So basically, describe decent memory BIST implementation is. So you need to give this answer. So basically, this orange color portion, what you see here is, these are the memories. These are actually the memories. So now, basically what happens is, in this memory, in this diagram, there are actually two cores. So it is actually separated by dotted lines. There are actually two cores, and memories are there in two different cores. Okay, and each memory, it should have a memory interface. So this blue color portion, what it is marked here as memory interface, this is what is called as the memory interface. So in the interface of memories, we will be having some muxes in order to select between the test input and the functional input. We'll see in the next topic. Okay, so this is the memory interface. Now this memory interface, it will be driven by this TMB. So TMB is called as the Descent Memory BIST controller. So these interfaces, they will be driven by this TMB. TMB stands for Descent Memory BIST controller. Okay, and this Descent Memory BIST controllers, they are actually controlled by BAP. BAP stands for BIST access port. Okay, BAP stands for BIST access port. And now what happens is, this tab, so here you will be having this TDI. So what will happen is, this tab, it will actually control this BAP through the SIP. Okay, so inside this BAP only we have the TDR. TDR is nothing but test data register. So the required data, what has to be written onto this test data register, it will be written through this TDI. So this tab, it will be controlling the BAP through SIB. That is, if SIB is open, if the SIB is programmed with 1, it is open, and hence it will pass the value to the BAP. If the SIB is closed, that is, if it is programmed with 0, then the data, it will not be written onto the BAP. So this is how it happens. This is what is decent memory BIST implementation. You'll be able to understand these things clearly when we complete the JTAG topic, IJTAG topic, everything after completing step by step. When you come here, when you come back here, you will be able to understand clearly. Again, I'll be explaining all these things as well. So this is just a demo class. So just a demo question alone I am telling. Okay, you'll be able to understand it clearly once we have completed JTAG, IJTAG, and when we come to MBIST, you'll be able to understand it clearly. So as of now, just remember, like this tab, it will be controlling this BAP through this SIB. That is, if the SIB is programmed with 1, if SIB is programmed with 1, then it will allow the data to be written onto the BAP. If the SIB is programmed with 0, then it will not allow the data to be written onto the BAP. Okay, so this is what is there. This is what is test memory BIST implementation. So you'll be able to understand it clearly when we complete JTAG, IJTAG, and when we come to MBIST, you'll be able to understand clearly. This is just a sample question. Again, I will be explaining these questions as well in the original course. Okay. So let me just write down the points here. So in this diagram, in this diagram, memory blocks, memory blocks are instantiated in two different cores, within the chip. So each memory must have a memory interface. Each memory should have a memory interface, So what is a memory interface we will see next. Then these interfaces are driven by Tessent memory BIST controllers. So these are the controllers are controlled by BAP. So in this BAP, the full form of BAP is BIST access port. So the tab, which is the IEEE 1149.1 standard, controls the BAP through the SIP. So what will happen is, when SIP is opened means SIP is programmed with 1. SIP is programmed with 1. It passes data to the BAP, which then generates the test commands to the memory BIST controller. So basically, like, there are two signals actually here. So for carrying out MBIST, we actually require two signals. One is BIST setup signal. It has to be it is a 2-bit signal. It has to be made 0 1, and there is another signal called as BIST PG enable. So that has to be made 1. Only then the memory BIST operation will actually start. So in order to control these signals, in order to write appropriate value onto these signals only, what will happen? So that appropriate value of those two signals, it will be coming from this tab. So through the SIP, if the SIP is programmed with 1, then the appropriate value of those two signals will be written onto the BAP, and from the BAP it will be controlling the controller. So only when the BIST setup signal is 0 1 and BIST PG enable is 1, only then the present memory BIST operation will start and the algorithms will actually start. Okay. So that is what happened. That appropriate value of BIST setup signal and BIST PG enable signal. So that will be actually coming here. Through this tab it will be written, and if the SIP is programmed with 1, it will allow the data to be written onto BAP, and inside this BAP you have the TDR. So that TDR, test data register, only will be, the output of this BAP will only be controlling those two signals. Okay. So when this SIP will be programmed, how it will be programmed, all these things, right? When we discuss the JTAG topic, you will be able to understand it more clearly. So again, I'll be covering all these questions. So now you might feel like it is like a little bit difficult, but once we have completed JTAG, IJTAG, and when we come to MBIST, you will be able to understand it clearly. So here basically now what happens is, this is the present memory BIST implementation, and after this you can even tell how the memory BIST is actually done. So I was just talking about these two signals. This BIST setup signal, it has to be made 0 1, and BIST PG enable signal has to be made 1. only then. So this is actually going as an input to the memory BIST controller. Okay, these signals, it is actually going as an input to the memory BIST controller. So these are basically static signals. This will be the same throughout the run. So these signals, it will actually be controlled by this JTAG network actually. So what is happening is the tag, through the tag, the appropriate value of these signals, it will be written into the TDR through SIP. That is, it will be written onto the back through the SIP. When SIP is opened, it will allow the data to be written onto the back. And the output of the back, it will be going to the controller. That is, it will be the output of the back, it will be controlling these signals to the appropriate value. So this is what happens. So these signals, they are actually controlled by the back. Controlled by back. So that is what was told in the previous slide. Okay. So now what will happen is, if you see here, this is the memory interface. So this yellow color portion, this one, this is only the memory interface. So in this memory interface, so here we had seen, right, this memory interface, this is only this interface. Okay, so this memory is surrounded by memory interface. So in this memory interface, what we are actually having is, we are having muxes. So if you closely see in the memory interface, we are actually having muxes. So if you closely observe these muxes, they are going to select between functional input and test input. This is what is from memory BIST controller, whatever value it is coming, that is the test input. So it is going to select between the functional input and test input based on this BIST on signal. This BIST on signal is only going as a select line for the mux. So this BIST on signal, based on the BIST on signal, uh, this muxes, it will select between the functional input and the test input. Okay. So when this BIST on signal, when this BIST on signal is 1, then that means it is going to select the test input. When BIST on signal is 0, then that means it is going to select the functional input. Okay. So this is what is there in the interfaces. So now here what happens is, first we'll see the memory interface. So the memory interface would select either to apply a functional input or test input based on signal. Based on signal. So this BIST on signal, from where this BIST on signal is controlled, this BIST on signal, if you see, it is controlled by an FSM which is present in the memory BIST controller. Okay. So BIST on signal is controlled by the FSM which is inside memory BIST controller. Which is inside memory BIST controller. Okay. So as I told, when BIST on signal, when it is 0, so it is, which means it is in functional mode, it will select the functional input. When BIST on signal is 0, BIST on signal is 1, then that is in BIST mode and it will select test input. Now we are going to focus on when BIST on is going to be 1. Okay, when BIST on is 1, what happens, we are going to see. So when memory is in BIST mode, memory is in BIST mode, that is when BIST on signal is 1. It starts the BIST algorithm. So there will be various algorithms actually. We will discuss few small algorithms like 0-1 algorithm, checkerboard algorithm, and then those March algorithm, Max algorithm. So some small algorithms we can see, and how it will detect the faults. Various faults in memories also it will be covered, like coupling faults, neighborhood pattern sensitive fault, stuck at fault, transition fault. So those faults also will be covered. Okay, and how these algorithms they will be covering the fault we will see. But in decent memory based implementation, like some complex algorithms will be used, like S-March checkerboard BCD algorithm. So those are like big algorithms. So the sequence itself will be like 1 or 2 pages. So those algorithms you will be like able to get it from the decent manual. So I'll also tell you from in which like where you need to check for those algorithms in the descent manual. So we will discuss those things in our like original this interview preparation course. Okay. So basically we will see now when memory is in BIST mode, it starts the BIST algorithm. So what happens is, let me just take a copy of it. So what basically happens is, this FSM and the signal generator, both these things, this FSM and signal generator, what it will do is, it will write a value onto the memory. So it will write a value onto the memory, okay, and it will also write the same value onto the comparator. Okay, so this FSM and signal generator, these two, according to the algorithm, they write a value onto the memory, and they also write the same value onto the comparator. So this value is what is called as expected value. Whichever value is directly written onto the comparator, this is the expected value. So this will be the expected value. And then what will happen is, the output of the memory, now the value has been written into the memory, right? The output of the memory, again it will be given to the comparator. So this is in the diagram there are two comparators, because comparator it can either be placed in the interface or it can be placed in the controller. So both options are possible, that is why they have kept two comparators actually. Okay, so it is like this actually. It can either be placed in the interface or it can be placed in the controller. So that one, which one is more advantageous, why it is more advantageous, that we will discuss it in our course. Okay. So the output of the memory, it is actually given to the comparator. This is actually called as the actual value. Okay. So the FSM and the memory interface, they will write a value onto the memory as, sorry, FSM and the signal generator. The FSM and the signal generator, they will write a value onto the memory, and they also write the same value onto the comparator. And then the output of the memory, it will again be given to the comparator. Now, this expected value and this actual value will be compared in the comparator. So if expected value and actual value are same, then that means the test is passed. And expected value and actual value both are different, then there is some fault in the memory. So this is how the memory faults will be detected. Okay, the faults in the memory will be detected. So what are all the possible faults in the memory? How it will be detected by the algorithms? Those things we will discuss it during our course. Okay. So the FSM here, what happens? The FSM plus the signal generator, writes the value onto the memory, and also to the comparator. So to the comparator. So the value in comparator, it is the expected value. value in comparator. This is the expected value. Now what happens? The output of the memory, the output of memory. So this is the actual output, actual value or actual output something is also given to the comparator. Given to the comparator, which compares the actual output and the expected output. Compares the actual output and the expected output. So if actual output is equal to expected output, which means test is passed, there is no problem in the memory. If actual output is not equal to expected output, and that means there is some problem with the memory and test is failed. So just for an example I'm telling, like say for example this signal generator and FSM, they have written a value 0 into this memory cell, and the in the comparator also 0 is actually written, but there is some fault in the memory, like some coupling fault or some fault is there in the memory. So because of which whatever 0 has been written, it suddenly got changed to 1. Okay, there will be like various faults, coupling faults, those things will be there, because of which the value 0 what was written onto the memory has got changed to 1. Now this value output of the memory will be read and it will be compared in the comparator. So now expected value is 0, but the output of the memory is 1, which means there is some fault in the memory. Okay, there is some fault in the memory, we can tell. So now if there was no fault in the memory, then whatever value it has written, the same value it will be like output will be coming as output from the memory. Then when both are compared, both are same, that means there is no problem with the memory. So this is how the memory BIST testing will be done. Memories will be tested using test and memory BIST. Okay. So we will discuss it in depth, the various faults, memory faults which will occur, and also like the memory test and memory BIST operation protocol. That is this setup signal, BIST PG enable signal. What is this go bit? What is this done bit? So all these things we will discuss it in depth, and also like there will be a feature called as reduced address count. So what is that reduced address count feature, and why is the tool turning it on during like pre-silicon testing? So before manufacturing, while generating the patterns, why is the tool enabling that feature? So those kind of things, some interview questions will be there, and also this comparator placement. This comparator, it can either be placed in the memory interface or it can be placed in the memory BIST controller. So which one is more advantageous? Why it is more advantageous? And then like there is one concept called as grouping of memories. So all these concepts we will be discussing it in depth in our this one course. We will discuss it. So this was what is our demo. So few questions I have discussed. I will again discuss all these questions as well when we are like dealing in our original course, that particular topic when we are seeing. I will again discuss all these questions as well. Okay. So other questions like, yeah, in OCC you might OCC some questions might be asked, and there is a topic called as scan wrappers. So from there that those questions might be asked, and some questions related to like hierarchical scan. What is the difference between top down approach, bottom up approach? Bottom up is only hierarchical scan. So those things they can ask in the interviews. So this was a demo session, and in next week's class we can start with scan insertion. We'll start scan insertion and we'll try to like cover most of the interview questions which is asked in scan insertion topic. And Saturday and Sunday, next week Saturday and Sunday, we will try to complete the scan insertion topic, the interview questions related to that topic. So each week we will target one topic and we try to complete the questions from that topic. And ATPG and all, it will take some 1.5 weeks to cover because many topics are there. 1.5 weeks or 2 weeks to cover ATPG. So like 3 or 4 classes will be required because many topics are there in ATPG. But the same thing when it comes to simulation, it can be completed in 1 or 2 classes. So this is also each topic we can cover it in either based on the length of the topic. So EDT and all, it can be covered quickly, but when it comes to scan, it might take some more time. So based on the length of the topic, we can try to cover it up within 2 classes or maximum 4 classes. We can try to cover the interview questions of each topic. So minimum 2 classes, maximum 4 classes. So we'll try to cover the interview topics, interview questions of those topics, and from next week we can start with our session. So do you have any doubts? And forward you your attendance. You can fill it up.